Humanity likes to think it's pretty smart. We've split the atom, decoded the genome, and created a global network that lets you watch cat videos at 3 a.m. But for all our accomplishments, there's an overwhelming amount of stuff we just don't know. Let's start with space because it's big, empty, and filled with stuff we don't understand. And topping the list of cosmic mysteries is dark matter. Dark matter makes up about 27% of the universe, yet it's completely invisible. It doesn't emit, reflect, or absorb light. It doesn't interact with electromagnetic forces. And as far as we know, you can't touch it, see it, or smell it. And yet, its gravitational effects shape the entire structure of the cosmos. We know dark matter exists because galaxies spin way faster than they should, based on the visible matter we can observe. If regular matter, stars, planets, dust, and gas was all there was, galaxies would tear themselves apart. The only explanation is that there's something else, something massive, creating additional gravitational pull and holding everything together. But what is dark matter made of? Well, we don't know. And that's where things get weird. Scientists have been hunting for dark matter for decades, and they've come up with a few possible contenders, like weakly interacting massive particles. These hypothetical particles have mass and interact via gravity and possibly the weak nuclear force, but otherwise they just pass through regular matter like a ghost through walls. Despite their popularity as a dark matter candidate, WIMP detectors, including massive underground experiments, have come up empty so far. Axions are ultralight particles that could solve some problems in quantum chromodynamics because apparently we didn't have enough problems. Axions could also form a type of dark matter, but like WIMPs they remain purely theoretical and undetected. We already know about 3 types of neutrinos, tiny, almost massless particles that barely interact with matter. A sterile neutrino would be an even more elusive version, only interacting through gravity. It's a compelling idea, but evidence is scarce. Some physicists wonder if dark matter might actually be a collection of ancient black holes formed just after the Big Bang. These would be incredibly small compared to regular black holes, but still pack a gravitational punch. The problem, we haven't seen them either. But what if dark matter doesn't exist at all and we just don't understand gravity as well as we thought? Some theories, like modified Newtonian dynamics, suggest that our equations for gravity might break down on cosmic scales. It's an intriguing idea, but so far the evidence still leans in favor of a dark matter hypothesis. We've built detectors deep underground, shielded from cosmic rays, hoping to catch dark matter particles in action. We sent satellites into space to map the gravitational effects of dark matter across the universe. We've smashed particles together at near light speeds in the Large Hadron Collider to see if we can create dark matter in a lab. And yet, nothing. Dark matter is out there, shaping galaxies, bending light, and making up a massive chunk of the universe. We just haven't figured out what it is yet. If dark matter wasn't confusing enough, meet dark energy, the cosmic curveball that makes up a staggering 68% of the universe. Discovered in the late 1990s, dark energy is the force driving the accelerated expansion of the universe. Imagine blowing up a balloon, and instead of slowing down as the rubber stretches, the balloon starts inflating faster on its own. That's the universe, and we have no idea why it's happening. Before dark energy was discovered, most physicists assumed that the expansion of the universe, set in motion by the Big Bang, would eventually slow down due to gravity. But observations of distant supernovae revealed the opposite. The universe's expansion is speeding up. Something is pushing galaxies away from each other with increasing force, and we call that mysterious something, dark energy. As with dark matter, there's no shortage of ideas about what dark energy might be. One leading theory is that dark energy is an inherent property of empty space. According to quantum field theory, even a perfect vacuum is teeming with virtual particles popping in and out of existence. This vacuum energy could exert a repulsive force, driving the accelerated expansion of the universe. Originally proposed by Einstein, and later called his biggest blunder, the cosmological constant, is a term added to his equations of general relativity to allow for a static universe. When the expansion of the universe was discovered, the cosmological constant made a comeback, but now as an explanation for dark energy's repulsive force. Some theories propose that dark energy's effects arise from hidden dimensions predicted by string theory. These extra dimensions could exert influence on the observable universe in ways we don't yet understand. Quintessence is a hypothetical dynamic field that changes over time, unlike the cosmological constant's fixed value. Quintessence could explain why the rate of expansion seems to vary across different eras of cosmic history. Here's the terrifying one. If dark energy keeps accelerating the expansion of the universe, there's a scenario where it eventually overcomes all forces of attraction, tearing galaxies, stars, planets, and even atoms apart. This hypothetical end of everything is known as the Big Rip. We measure dark energy's effects through the cosmic microwave background, the distribution of galaxies, and the redshift of supernovae, and the evidence keeps piling up. But what dark energy actually is remains one of the biggest mysteries in cosmology. It's a force that shapes the fate of the universe, yet it's completely invisible and doesn't interact with anything we can detect directly. Between dark matter and dark energy, we're looking at about 95% of the universe made up of stuff we can't see, touch, or fully explain. Everything we know, from stars and planets to trees and tacos, is just 5% of the total cosmic pie. The rest remains an enigma. Our best theories hint at exotic particles, hidden forces, and possibly even entirely new dimensions. And yet every time we build a more sensitive detector or launch a more powerful telescope, the universe seems to get even more confusing. What happened before the Bang? We've gotten pretty good at explaining what happened after the Big Bang, how matter and energy cooled and clumped together to form galaxies, stars, and everything we know. But the moments before the Big Bang, that's where things get incredibly weird. It's a total black box, one that scientists have been trying to pry open for decades. Imagine showing up at a party and it's already in full swing. People are dancing, the music's loud, and the snack table's half empty, but nobody knows who started the party or when it began. That's kind of how we feel about the universe. We're living in it, observing its expansion, measuring its age. But the question of what came before remains one of the greatest unsolved mysteries in physics. The Big Bang wasn't just an explosion of matter, it was the beginning of space and time itself. Before the Bang, there was no before in the traditional sense, because time as we know it didn't exist. This makes asking what came before tricky, because we're limited by the very framework of time that the Big Bang created. One leading idea is that our universe is just one bubble in a vast multiverse. The idea that the universe underwent a period of rapid expansion right after the Big Bang, and that this expansion could be happening forever in other parts of reality. Imagine a pot of boiling water. Each bubble that forms is a universe, and our universe is just one of them. New bubbles keep forming, and some might have different physical laws or dimensions. This theory opens the door to an infinite number of universes, some similar to ours, some radically different. But if that's the case, what's driving this eternal inflation? And what created the pot of water in the first place? They don't know. Every answer seems to raise more questions. Maybe the universe isn't a one-time event. The cyclic model suggests that the universe goes through infinite cycles of expansion and contraction. a cosmic big bounce rather than a single bang. In this theory, the universe expands, reaches a certain point, and then collapses back into a singularity before bouncing back into a new expansion. This cycle repeats endlessly. It's an elegant idea, but we haven't yet found conclusive evidence of previous bounces. One of the more mind-bending possibilities is that the universe literally came from nothing. Thanks to the strange world of quantum mechanics, particles can pop in and out of existence without any apparent cause. It's possible that our universe began as a quantum fluctuation, a tiny blip of energy that expanded into everything we see today. But then we hit a philosophical roadblock. What is nothing? Even empty space has energy and quantum fields. So where did the quantum laws come from? According to string theory, our universe might be a three-dimensional brain floating in a higher dimensional space. The Big Bang could have been the result of a collision between two brains, like two sheets of paper slapping together. This would explain the sudden release of energy that kicked off the universe's expansion, but it also raises questions about what these higher dimensions are and what exists beyond them. What if the question of before the Big Bang doesn't make sense because time itself is a construct? Some physicists propose that time is emergent, not fundamental, an effect of the entropic properties of the universe. In this view, the Big Bang was just the point where our particular configuration of entropy started increasing. Before that, there may have been different states of existence where the concept of time didn't apply. One of the biggest problems in exploring what came before the Big Bang is that our current physics breaks down at the singularity, the point of infinite density where time and space begin. Our most advanced models, general relativity and quantum mechanics, stop working when we approach this point. To understand the pre-Bang universe, we likely need a theory of quantum gravity, a single framework that unites the large-scale laws of gravity with the small-scale behavior of quantum particles. We don't have that yet, though string theory, loop quantum gravity, and other contenders are trying to fill that gap. What happened before the Big Bang remains one of the deepest and most perplexing questions we can ask. Every theory we've proposed brings fascinating possibilities, from endless cycles of creation and destruction to multiverses and higher dimensions. But for now, the truth remains just beyond our grasp. And maybe that's okay. The search for answers pushes the boundaries of human knowledge and sparks new ideas and unexpected discoveries. One day, we might uncover what started the party. Until then, we'll keep dancing. Why does time flow? Time is weird. It's one of those things we all experience constantly but barely understand. We perceive it as a one-way street, always moving forward, dragging us along with it. But the laws of physics don't actually require time to move in any particular direction. They work just fine whether time runs forward or backward. So why does time have a direction? Why can we remember the past but not the future? Why does it seem like we're stuck in a constant march toward tomorrow? One of the most widely accepted explanations for why time flows forward is entropy, the tendency of systems to move from order to disorder. Imagine breaking a glass. It shatters into a million pieces, and those pieces scatter randomly. You never see a broken glass suddenly reassemble itself. That's entropy in action. Entropy is a principle of the second law of thermodynamics, which states that the total entropy of a closed system can only increase or stay the same. It's why your coffee gets cold, why your room gets messy, and why people age. This gradual drift from order to chaos creates a natural distinction between the past, where things were more orderly, and the future, where things get more chaotic. That's one way we explain the arrow of time, the direction in which entropy increases. But there's a catch. The laws of physics themselves, from Newtonian mechanics to quantum field theory, don't actually demand this one-way movement. They work perfectly well if time ran backward. So why does entropy increase in only one direction? And why did the universe start in such a low entropy, highly ordered state? That's one of the great unsolved questions of physics. Some physicists suggest that time might not be a fundamental aspect of reality at all. It could be an emergent property of quantum interactions. Think of temperature. Individual molecules don't have a temperature on their own, but their collective motion creates heat. Time, in this view, could be a similar byproduct of deeper processes happening at the quantum level. Quantum gravity theories like quantum gravity and string theory propose that time might emerge from the way particles and fields interact on incredibly small scales. In this sense, our perception of time as a smooth, continuous flow might be an illusion created by underlying quantum mechanics. Could time ever flow backward? In some theoretical models, the answer is yes. Certain interpretations of the multiverse theory suggest that in different universes, time might flow in different directions. There's also speculation that during phenomena like the Big Crunch hypothetical scenario where the universe collapses back in on itself, time's arrow could reverse. Even within our universe, there are time reversal symmetry experiments in particle physics. Certain subatomic particles, cons, exhibit behaviors that seem to violate this symmetry, providing tantalizing hints that the flow of time might not be as rigid as we think. But here's a truly mind-bending idea. Time itself might not exist in a fundamental sense. Julian Barber, a physicist and author of The End of Time, argues that what we perceive as time is just a series of distinct nows, snapshots of the universe in different states. Our sense of time flowing is merely the way our brains interpret the relationships between these states. This concept aligns with block universe theory, where the past, present, and future all exist simultaneously in a four-dimensional block of space-time. In this model, time doesn't move, we just experience it, subjectively, like watching frames of a movie. Another layer of the mystery is the role of consciousness in our perception of time. Why do we experience time as a continuous flow? Neuroscientific studies suggest our brains assemble sensory information into a coherent narrative, smoothing out the gaps and delays in perception. This process creates our subjective experience of time, but it may not reflect an objective reality. Time dilation experiments in relativity theory show that time's passage depends on factors like gravity and velocity, further proving that time isn't a universal constant. An astronaut traveling near the speed of light would experience time far more slowly than someone on Earth. So, which version of time is real? The truth is, we don't know why time flows, or if it even flows at all. Entropy gives us a practical framework, but deeper mechanics remain elusive. Time might be an emergent property, a quirk of quantum physics, or even an illusion created by our consciousness. It could run differently in other universes, reverse under extreme conditions, or not exist in any fundamental sense. Time travel has been a fixture of science fiction for decades, but it's also a serious question in physics. The nature of time itself, and whether we can move through it in more than one direction, remains one of the greatest mysteries in science. Despite the countless books, movies, and TV shows that have explored the concept, the real science behind time travel is even stranger and more complex than fiction often portrays. The implications of unlocking time travel go beyond simple curiosity. They touch on the foundations of causality, the structure of the universe, and even the nature of reality itself. Einstein's theory of relativity already shows us that time is not fixed. It stretches and contracts depending on speed and gravity. This has been confirmed by experiments with atomic clocks. One placed on a fast-moving plane ticks slower than one on the ground. This effect, called time dilation, means traveling forward in time isn't just possible, it's happening all the time, just at a minuscule scale. Astronauts on the International Space Station, moving at high speeds, age slightly slower than those of us on Earth. Over long enough journeys at near light speed, an astronaut could experience days while years pass on Earth. This effect has profound implications for interstellar travel, suggesting that future explorers could return home to find centuries have passed. But moving backward, that's where things get weird. Solutions to Einstein's equation suggest that closed time-like curves, essentially paths through space-time that loop back on themselves, could theoretically exist. These curves could allow someone to travel back to an earlier point in their own timeline. However, this runs into the infamous paradoxes of time travel. The grandfather paradox. What happens if you prevent your own existence? And the information paradox. Where does knowledge come from if it's passed backward in time? There's also the ontological paradox, where objects or information have no clear point of origin because they exist in a causal loop. These paradoxes challenge our understanding of cause and effect and raise questions about the consistency of the universe. Wormholes, Einstein-Rosen bridges, are another theoretical pathway to the past. These hypothetical tunnels through space-time could connect distant points or different times. But keeping a wormhole stable enough for travel would require exotic matter with negative energy density, something we've never observed. Even if we could locate or create a wormhole, manipulating it to connect specific points in time would be a monumental challenge. Some physicists suggest that even if wormholes exist, they might only allow travel between the moments when they were created and when they collapse, limiting their usefulness as time machines. Moreover, the creation of such a wormhole will likely require energy on a cosmic scale, far beyond anything humanity can currently generate. Quantum mechanics also offers tantalizing hints. The phenomenon of quantum entanglement suggests faster-than-light interactions, though it doesn't directly imply time travel. Some interpretations of quantum theory, like the many-worlds hypothesis, suggest that changing the past would simply create a new, branching timeline, rather than altering the one we came from. This idea provides an elegant solution to the paradoxes of time travel, as each trip to the past would create an alternate universe where different events unfold without affecting the traveler's original timeline. This also opens the door to the idea that infinite parallel realities might exist, each with their own distinct histories and futures. Practical time travel remains beyond our reach for now. Even if the physics checks out, the engineering challenges are staggering. We need enormous amounts of energy, exotic materials, and control over forces we barely understand. The energy required to manipulate space-time on this scale is currently far beyond our technological capabilities. Some speculative ideas propose harnessing black holes, cosmic strings, or rotating cylinders of ultra-dense matter, but all of these remain purely theoretical. There's also the question of safety. Would traveling through time expose travelers to dangerous levels of radiation, extreme gravitational forces, or unknown quantum effects? Still, the possibility remains tantalizing. If backward time travel is ever proven possible, it would upend our understanding of causality and the universe itself. The implications for history, ethics, and even personal identity would be profound. We'd have to reconsider how we think about free will and determinism, whether the past could ever truly be changed. And who knows, maybe time travelers are already among us, and we just haven't noticed. Or perhaps they're being very careful not to disrupt the timeline in ways we'd recognize, blending seamlessly into the flow of events as we know them. The mystery of time travel captures our imagination because it challenges the very limits of what we believe is possible, and the answers may redefine everything we know about existence. Quantum physics is where common sense goes to die. The rules that govern the everyday world, the kind that let you throw a baseball or boil an egg, simply don't apply at the subatomic level. Particles behave like waves. Waves behave like particles. Things exist in two places at once. A particle's state isn't even real until you measure it. If that sounds like magic, you're not far off. Particles can be in two places at once, influence each other instantaneously over vast distances. But why does the quantum world behave so differently from the macroscopic world we experience? The problem isn't just that we don't understand the quantum realm. It's that every attempt to explain it raises deeper, weirder questions. The Copenhagen interpretation suggests reality doesn't exist until we observe it. The many worlds theory posits that every quantum event spawns parallel universes. Pilot wave theory tries to add hidden variables, but those only push the mystery further back. Let's start with the wave-particle duality. Light acts like a wave and a particle. So do electrons, protons, and pretty much every fundamental particle. This was proven by the famous double-slit experiment, where single particles fired at a barrier with two slits somehow create an interference pattern, something waves do. But here's where it gets nuts. If you observe which slit the particle goes through, the interference pattern disappears, and the particle acts like, well, a particle. This suggests that reality changes based on observation. Does that mean the universe only exists when we look at it? Nobody knows for sure. Quantum entanglement is where Einstein himself tapped out and called it spooky action at a distance. When two particles become entangled, their states become linked no matter how far apart they are. Change one, and the other instantly changes too, even if they're light years apart. This defies the idea that nothing can travel faster than light. Yet entanglement has been repeatedly confirmed in experiments. How do particles communicate faster than light? Are they sharing information through extra dimensions? Or is our understanding of space and time just incomplete? Since the math of quantum mechanics works, but the implications are bizarre, scientists have tried to interpret what it all means. Unfortunately, every interpretation is weirder than the last. The most widely taught version, and the one that makes the least sense, suggests that particles exist in a state of superposition, multiple states at once, until they're observed. Reality, in this view, is a bit like a choose-your-own-adventure book, except the adventure doesn't exist until you pick a page. Every time a quantum event happens, the universe splits into multiple timelines. If you flip a quantum coin, in one universe it's heads, and in another it's tails. This creates an infinite number of parallel universes where every possible outcome exists. The pilot wave theory tries to make quantum mechanics deterministic again, by suggesting that particles follow invisible guiding waves. But this just kicks the weirdness can down the road, because now we have hidden variables we can't detect. If the quantum realm is where common sense dies, black holes are where physics itself breaks down. These objects are so massive and dense that their gravity warps space and time into something unrecognizable. A black hole's event horizon is the point of no return. Cross it and you're never coming back. Even light can't escape. But the real mystery lies inside. At the core of a black hole is a singularity, a point where infinite density causes space-time to collapse. Our current physics can't describe what happens here. One of the biggest puzzles surrounding black holes is the information paradox. In quantum mechanics, information can't be destroyed. The state of any system should always be recoverable. But black holes seem to swallow information permanently. Stephen Hawking proposed Hawking radiation, a form of thermal radiation that black holes emit, suggesting they slowly evaporate over time. But if the black hole disappears, so does the information. This violates one of the core principles of quantum mechanics. Recent ideas, like the holographic principle, suggest that all the information that falls into a black hole might be encoded on its surface, like a cosmic hard drive. But this theory remains unproven. Another issue is the black hole firewall paradox. Quantum theory suggests that if you fell into a black hole, you'd experience spaghettification, being stretched into a long, thin strand by gravitational forces. But some calculations suggest you'd hit a wall of high-energy radiation at the event horizon, a firewall, and be incinerated instantly. Both scenarios are terrifying and mutually exclusive, and we don't know which, if either, is right. If black holes consume everything, white holes would be their opposite, spewing matter and energy while nothing can enter. They're a purely theoretical concept, but some scientists wonder if the Big Bang itself was a kind of white hole event. Both the quantum realm and black holes suggest that we're missing something fundamental about reality. They hint at deeper laws of physics waiting to be discovered, possibly involving extra dimensions, new forces, or an entirely different understanding of space-time. The quest to understand these mysteries pushes the boundaries of human knowledge and inspires some of the most ambitious scientific efforts of our time. Whether it's smashing particles together at the Large Hadron Collider or peering into the depths of space with the James Webb Telescope, every discovery takes us closer to answers and raises new questions. For now, the quantum realm of black holes remain two of the biggest frontiers of the unknown and the ultimate test of how far our curiosity can take us. When we talk about the size of the universe, we quickly run into the limits of human comprehension. Numbers like 93 billion light-years sound massive, and they are, but they only describe the observable universe, the tiny slice of reality where light has had time to reach us since the beginning of the cosmos. What lies beyond that? We have no idea, and possibilities are as mind-bending as they are mysterious. Let's start with the observable universe. It's a sphere roughly 93 billion light-years across, centered on Earth. This is the distance light has traveled since the Big Bang, about 13.8 billion years ago. But wait, if the universe is 13.8 billion years old, shouldn't the observable universe only be 27.6 billion light-years across? Not quite. The universe has been expanding this whole time, meaning distant galaxies have been carried away from us at incredible speeds. As a result, the space between us and those early light sources has stretched, making the observable universe far larger than a simple calculation would suggest. But the observable universe is just that, observable. It's limited by the speed of light and the age of the universe. What's beyond that boundary? There's no reason to believe the universe just stops at 93 billion light-years. In fact, most cosmologists think it goes on much farther, maybe infinitely far. The question of whether the universe is infinite or finite remains open. An infinite universe would mean space stretches on forever, with no edge or boundary. This idea comes with its own weird implications. In an infinite universe, every possible configuration of matter must eventually repeat. That means there could be other regions of the cosmos that look exactly like our observable universe, maybe even exact copies of Earth, you and me. On the other hand, the universe might be finite but unbounded, like the surface of a sphere but in higher dimensions. In this scenario, if you travel far enough in one direction, you'd eventually end up back where you started. This raises the possibility that the universe could loop back on itself in ways we can't currently detect. Then there's the idea of the multiverse. If our universe is just one bubble in a vast cosmic foam, there could be countless other universes out there, each with its own laws of physics and fundamental constants. Some of these universes might be radically different from ours, with entirely different kinds of matter, forces, and even dimensions, while others might be eerily similar. We've also considered the idea that the true size of the universe might be hidden by the nature of space-time itself. Some models suggest that space could be folded or warped in ways that create hidden dimensions or parallel spaces that we can't directly observe. String theory, for example, posits that extra dimensions could exist beyond the three of space and of time that we experience. In short, the true size of the universe remains one of the greatest mysteries in science, whether it's infinite, looped, or part of a larger multiverse. What we've seen so far is likely just a tiny piece of a much grander and more complex reality. Every discovery we make pushes the boundary of our knowledge a little farther, but the horizon of the unknown always stretches beyond our reach. The question of whether we are alone in the universe is one of the most profound and unsettling mysteries humanity faces. Given the sheer size and age of the cosmos, the apparent absence of extraterrestrial life raises more questions than it answers. This puzzle is encapsulated in the Fermi paradox, named after physicist Enrico Fermi, who famously asked, "Where is everybody?" For some numbers on this. Our galaxy, the Milky Way, contains an estimated 2 billion stars. Many of these stars have planets, and recent observations suggest that a significant portion of those planets reside in the so-called Goldilocks zone. Not too hot, not too cold, but just right for liquid water and potentially life. Expand this across the observable universe's estimated 2 trillion galaxies, and the potential for life becomes staggering. The Drake equation attempts to estimate the number of detectable extraterrestrial civilizations. It factors in variables like star formation rates, the fraction of stars with planets, the likelihood of life developing, and the chances of intelligent, communicative civilizations arising. Depending on the numbers you plug in, estimates range from "we are completely alone" to "the universe should be teeming with life." And yet there is silence. We've been scanning the skies with radio telescopes for decades and have yet to detect an unambiguous signal from an intelligent alien civilization. This absence of evidence isn't necessarily evidence of absence, but it's puzzling given the vast number of potentially habitable worlds. One possible explanation for this silence is the Great Filter, a hypothetical stage in the development of life that is incredibly difficult to pass. This bottleneck could occur at various points: the emergence of life itself, the evolution of intelligent beings, or the survival of advanced civilizations. If the filter is ahead of us, we may face existential threats that most species fail to overcome, such as nuclear war, climate collapse, or artificial intelligence gone rogue. Alternatively, maybe the aliens know we're here but choose not to interfere. The zoo hypothesis suggests that advanced civilizations observe less developed species like us without making contact. Like cosmic wildlife conservationists, some even propose that we could be part of an elaborate simulation, with our universe serving as a controlled experiment. Perhaps the most unsettling possibility is the dark forest theory, inspired by Lou Cixous's science fiction novel. It posits that the universe is a dangerous place where civilizations stay silent to avoid attracting hostile attention. In this view, advanced species may perceive any detectable signal as a threat and respond with preemptive aggression. Maybe intelligent life really is rare. The rare Earth hypothesis argues that the combination of factors making Earth habitable is extraordinarily uncommon. Everything from our stable climate to the presence of a large moon stabilizes our axial tilt could be unique. On the other hand, the idea of panspermia suggests that life might spread through the universe via comets, asteroids, or even ancient alien probes. If life on Earth originated elsewhere, it's possible microbial life exists across the galaxy. We just haven't found it yet. Despite the silence, our search continues. Missions like the James Webb Space Telescope and upcoming exoplanet studies may detect biosignatures, chemical signs of life in distant atmospheres. Projects like SETI search for extraterrestrial intelligence, persist in scanning for signals. And let's not forget the possibility of microbial life closer to home on Mars, Europa, or Enceladus. What if we are alone? If it turns out we are truly alone, the implications are staggering. It would make humanity an incredibly rare and precious phenomenon, a responsibility we have yet to fully grasp. Alternatively, the discovery of intelligent extraterrestrial life would transform our understanding of biology, technology, and our place in the cosmos. So, where is everybody? The answer remains one of the greatest unknowns, one we may or may not solve in our lifetimes. When you look at the universe, you can't help but notice how incredibly well ordered it is. Stars burn at just the right temperatures to forge elements like carbon and oxygen. Atoms stick together with just the right amount of force to create stable molecules. Even gravity has exactly the right strength to pull things together without crushing them into oblivion. It's as if the universe was set up with incredible precision, like a cosmic Goldilocks zone. Everything is just right for life. And that's where the fine-tuning problem begins. The fine-tuning problem refers to the observation that the fundamental constants of nature, like the gravitational constant, the strength of electromagnetism, and the mass of fundamental particles, are perfectly balanced in a way that makes life and the universe itself possible. If any one of these constants were just a tiny bit different, the universe as we know it would collapse into chaos or fail to form at all. If the gravitational constant were even slightly stronger, stars would burn through their fuel too quickly and explode before planets could form. If it were weaker, stars wouldn't ignite at all, leaving the universe dark and lifeless. The strength of electromagnetic interactions determines how atoms bond to form molecules. If electromagnetism were too strong, chemical reactions would become unstable. Too weak, and atoms wouldn't hold together. The strong nuclear force holds atomic nuclei together. If it were just a fraction weaker, protons and neutrons wouldn't stick together, and no elements other than hydrogen would form. A tiny bit stronger, and stars couldn't produce the right balance of heavier elements. The cosmological constant controls the rate of expansion of the universe. Observations show it's fine-tuned to about 1 part in 10 to the power of 120. If it were any larger, the universe would expand so fast that galaxies, stars, and planets could never form. If it were smaller, the universe would collapse back in on itself almost immediately. This incredible balance raises the question, why do these constants have exactly the values they do? There's no obvious reason they should, and yet they do. That's the fine-tuning problem. Maybe we just got lucky. In this view, there's no deeper reason for these constants. They just happen to fall into the narrow range that allows a stable, life-supporting universe. But the odds against this are so astronomically high that many scientists and philosophers find this hard to accept. Perhaps our universe is just one of an infinite number of universes, each with its own set of physical constants. Most of these universes would be sterile and chaotic, but by sheer probability, at least one would turn out like ours, capable of supporting life. This idea is supported by some interpretations of string theory and quantum mechanics, but so far there's no direct evidence for other universes. The anthropic principle suggests that the universe appears fine-tuned because we exist to observe it. In universes where the constants weren't balanced so perfectly, there would be no life to question them. While this is a logical observation, it doesn't explain why these constants have the specific values they do. Some take the fine-tuning of the universe as evidence of a purposeful creator who set the constants precisely to allow life. This idea is more philosophical than scientific and remains a matter of debate. Perhaps there's a more fundamental theory we haven't discovered yet,
that explains why these constants have the values they do.
Just as the properties of atoms arise from deeper quantum mechanics, the fine-tuning of the universe might emerge from some unknown underlying principles. Scientists are working hard to understand why the universe is so perfectly calibrated. Experiments in particle physics, like those at the Large Hadron Collider, aim to uncover deeper laws of nature that could explain the values of fundamental constants. Cosmologists are studying the early universe to understand the conditions that set the stage for everything we see today. The fine-tuning problem remains one of the greatest mysteries in science. Whether the answer lies in a multiverse, undiscovered physical laws, or something even stranger. The fact that our universe works so perfectly is a clue that there's still much more to learn about the nature of reality. Why is there something rather than nothing? This is one of the most profound and unsettling questions humanity has ever asked, and it remains largely unanswered. It's a question that cuts across the boundaries of physics, philosophy, and metaphysics, touching on the very foundation of existence itself. Despite our advancements in science and our ability to explain much about the universe's behavior and structure, the question of why there is a universe at all, rather than an endless void of nothingness, remains a staggering mystery. At first glance, the existence of something, matter, energy, space, and time, might seem obvious because we take it for granted. But when you stop and think about it, the alternative is just as plausible. Why not nothing? The laws of physics, as we understand them, don't necessarily require the existence of anything. In fact, the emergence of something from absolute nothingness poses a challenge to every explanatory framework we have. One possible approach to this question comes from physics, particularly quantum mechanics, and cosmology. Some physicists suggest that the universe could have emerged from a quantum fluctuation, a random temporary change in energy that created the Big Bang. In quantum field theory, particles pop in and out of existence all the time due to these fluctuations, so it's conceivable that the entire universe could have been born from one such event. But this only pushes the question back. Why do quantum fields exist at all? Why are there laws of physics governing these phenomena in the first place? Another theory involves the concept of a multiverse, an infinite collection of universes with varying properties. In this view, our universe is just one of many, and the question of why there is something rather than nothing might be reframed as why there is this specific version of something. But even if the multiverse exists, it still doesn't answer why any universe exists at all rather than sheer emptiness. Philosophers have grappled with this question for centuries. Some propose the principle of sufficient reason, which argues that everything must have a cause or explanation. But applying this principle to the totality of existence itself leads to a paradox. If everything must have a reason, what's the reason for the existence of reality as a whole? Others suggest that existence might be a brute fact, something without any deeper explanation, simply the way things are. Theologians often approach the question by invoking the concept of a necessary being, an entity that exists by its very nature and whose existence provides the foundation for everything else. In many religious traditions, this being is God, conceived as the ultimate cause and explanation for why there is something rather than nothing. But this answer raises further questions. Why would a necessary being exist? And why would it create a universe with these particular properties? Even more speculative ideas suggest that the distinction between something and nothing might be an illusion. Some interpretations of quantum physics and information theory propose that reality could emerge from abstract mathematical structures or informational states, with existence being a kind of emergent phenomenon rather than a fundamental one. In this view, the universe could be a projection or manifestation of underlying patterns of information that don't require physical substance in the way we usually understand it. There's also the anthropic principle. The idea that the universe's properties appear fine-tuned for life, because if they weren't, we wouldn't be here to observe them. This line of reasoning suggests that the question itself may be limited by our perspective. We see a universe full of something because that's the only kind of universe observers like us could exist in. But this doesn't resolve the deeper mystery of why any conditions for existence arose in the first place. Ultimately, the question of why there is something rather than nothing sits at the very edge of human understanding. Like an existential cliff we peer over with no clear view of what lies below. It's a question that may never have a satisfying answer, or one that requires a paradigm shift in our understanding of reality itself. Until then, the existence of the universe remains both an incredible mystery and a profound reminder of how much we have yet to learn. Gravity is one of the most familiar forces in our everyday lives. It keeps our feet planted on the ground, the moon in orbit around the Earth, and the Earth circling the sun. And yet, compared to the other fundamental forces of nature, electromagnetism, the strong nuclear force, and the weak nuclear force, gravity is embarrassingly weak. To put this in perspective, the electromagnetic force between two electrons is about 10 to the 36th power times stronger than the gravitational force between them. That's a 1 followed by 36 zeros, a difference so huge it's almost impossible to grasp, despite its cosmic scale influence. Gravity is so weak on a local level that you can lift your car keys against the gravitational pull of the entire planet with just 2 fingers. So why is gravity so weak? This question, known as the hierarchy problem, has baffled physicists for decades. The universe doesn't usually do things without a reason, and the vast disparity between gravity and the other fundamental forces, electromagnetism, the strong nuclear force, and the weak nuclear force, suggests there's something deeper we're missing. One of the most compelling ideas is that gravity's weakness is the result of extra dimensions, realms of space beyond the familiar 3 length, width, height, and 1 of time. According to theories like string theory and brain world models, our universe could be a 4-dimensional brain, floating in a higher dimensional bulk. Gravity, unlike the other forces, might propagate through these extra dimensions, meaning that what we experience is just a diluted remnant of its full strength. It's like trying to hear someone shouting from another room. The sound exists, but most of its energy dissipates elsewhere. Another approach involves gravitons, hypothetical quantum particles that mediate the gravitational force, much like photons mediate electromagnetic forces. If gravitons interact with extra dimensions, they could spend most of their time outside our observable universe, explaining why gravity appears so weak here. There's also the possibility that our understanding of gravity itself is incomplete. General relativity describes gravity as the curvature of space-time caused by massive objects. But this classical theory doesn't mesh well with quantum mechanics. Some physicists suggest modifications to general relativity, such as massive gravity, where the graviton has mass, or emergent gravity, where gravity arises from underlying quantum interactions. These theories remain speculative, but they hint that gravity's true nature might be more complex than we realize. The holographic principle offers another mind-bending idea, the possibility that our 3-dimensional universe is a projection of information encoded on a 2-dimensional surface at the boundary of the cosmos. In this scenario, gravity's apparent weakness could arise from the peculiarities of this projection, like a shadow appearing less substantial than the object casting it. Finally, some physicists propose that gravity's relative weakness could be tied to dark matter or dark energy, the mysterious substances that make up most of the universe's mass energy content. If gravity interacts differently with these unknown components, it could explain the force's anomalous behavior. Solving the mystery of gravity's weakness isn't just an academic exercise. Understanding gravity's true nature could lead to breakthroughs in quantum gravity, string theory, and the search for a theory of everything, a unified framework that explains all fundamental forces. Until then, gravity remains an enigma, a force both omnipresent and elusive, shaping the cosmos while keeping its deepest secrets just out of reach. When we talk about reality, we tend to take a lot for granted. We assume the chair we're sitting on is solid, the world around us exists independently of our perception, and time marches forward in a predictable line. But when we peel back the comforting layers of everyday experience, reality becomes far weirder and more uncertain than we could ever imagine. At the most fundamental level, we don't actually know what reality is. Are we living in a physical universe, a mathematical construct, or a sophisticated simulation? Even our most advanced scientific theories, from quantum mechanics to string theory, only scratch the surface of this mind-bending mystery. Let's start with what we know, or think we know. Classical physics painted a picture of a universe made up of distinct, tangible objects governed by predictable laws. Modern physics tore that comforting vision apart. At the atomic and subatomic levels, particles behave more like waves of probability than solid objects. Electrons don't orbit nuclei like little planets. They exist in clouds of potential positions until we observe them. The discovery of quantum fields pushed this strangeness even further. The standard model of particle physics suggests that what we experience as particles, electrons, quarks, photons, are actually excitations in invisible fields permeating the universe. The Higgs boson, for instance, is an excitation of the Higgs field, which gives other particles mass. This raises the question, if everything we see and touch is just vibrations in invisible fields, is anything really solid at all? One of the most baffling aspects of quantum mechanics is the role of the observer. The famous double-slit experiment showed that particles like electrons behave like waves when not observed, creating interference patterns. But the moment we measure which slit the electron passes through, it behaves like a particle again, and the interference pattern disappears. This suggests that observation itself influences the behavior of matter, but why? Interpretations of this phenomenon vary. The Copenhagen interpretation argues that reality exists in a state of superposition, multiple potential outcomes, until observation forces it to choose one. The many worlds interpretation proposes that every possible outcome of a quantum event actually occurs, splitting reality into countless parallel universes. Pilot wave theory suggests hidden variables guide particles in ways we don't yet understand for decades. Physicists have sought a single framework that unifies quantum mechanics, which governs the very small and general relativity, which explains gravity and our scale cosmic structures. These two theories work incredibly well in their own domains, but they're fundamentally incompatible with each other. String theory attempts to bridge this gap by proposing that all particles are actually tiny vibrating strings of energy. Different vibrations produce different particles, but string theory requires extra dimensions, up to 11, and remains largely untested. Loop quantum gravity takes a different approach, suggesting that space-time itself is made of tiny, discrete loops of quantum information. This theory aims to reconcile gravity with quantum mechanics without requiring extra dimensions. But it too remains speculative. Is the universe a simulation? The simulation hypothesis, popularized by philosopher Nick Bostrom, suggests that our reality could be a highly advanced computer simulation. If technological civilizations eventually develop the ability to run incredibly realistic simulations of conscious beings, the argument goes, there would likely be far more simulated worlds than real ones. meaning we are statistically more likely to be living in one of those simulations. Some scientists take this idea seriously. There have even been proposals to test it by looking for glitches or patterns in physical laws that wouldn't occur in a base-level reality. So far, no definitive evidence supports this theory, but it's hard to rule out entirely. Some physicists and philosophers argue that reality itself is fundamentally mathematical. Max Tegmark's mathematical universe hypothesis suggests that the physical world isn't just described by math, it is math. According to this view, the structures and relationships that make up mathematics are the same structures and relationships that make up reality. This idea explains why mathematical equations so perfectly describe physical phenomena, from the motion of planets to the behavior of subatomic particles. But it also raises difficult philosophical questions. If reality is math, why do we experience it as anything else? And what generates this mathematical structure in the first place? Another possibility is that reality is emergent, arising from more fundamental processes we don't yet understand. Some theories suggest the universe is fundamentally made of information, with space, time, and matter emerging from complex interactions of quantum data. This ties into ideas like the holographic principle, which proposes that our three-dimensional universe might be a projection of information encoded on a distant two-dimensional surface. If true, this would mean everything we experience as solid and real is actually a kind of cosmic illusion. Even concepts as basic as time and space aren't as straightforward as they seem. In relativity, time is relative. It moves slower near massive objects and at high speeds. Some physicists argue that time itself might be an emergent property, rather than a fundamental feature of the universe. Then there's a question of why time flows in one direction. The arrow of time aligns with increasing entropy, the tendency of systems to move from order to disorder. But the deeper reason behind this asymmetry remains a mystery. In some models of the multiverse, other universes might experience time flowing backward, or in entirely different ways. No discussion of reality would be complete without addressing the nature of consciousness. We experience the world subjectively through thoughts, emotions, and sensations, but science still doesn't understand how or why this happens. The hard problem of consciousness, articulated by philosopher David Chalmers, asks why physical processes in the brain give rise to subjective experience. Some theories propose that consciousness is a fundamental property of the universe, like space and time. Others suggest it's an emergent phenomenon arising from the complexity of neural networks. Every step closer to understanding reality seems to reveal deeper layers of mystery, from quantum weirdness to the search for a unified theory, from the possibility of simulation to the enigma of consciousness. We are surrounded by questions we don't yet have answers to. But perhaps that's what makes this journey so compelling. The quest to understand reality pushes us to explore the unknown, challenge our assumptions, and expand the boundaries of human knowledge. Whether or not we ever reach a final answer, the search itself may be the most important part of the adventure.